Hi, good morning. Welcome to day 2 of the GESDA Summit. And with great thanks to the GESDA's stellar organization and also the wonderful speakers, I suspect your brains are filled with new ideas, ruminations, and inspiration. Dare I say, augmented. So today's agenda promises also an equally fortifying agenda. I'm Karen Rommelfanger, a neurotech ethicist and strategist. I co-founded and direct the Institute of Neuroethics Think and Do Tank, the world's first international think and do tank wholly dedicated to neuroethics, where our mission is to create transformative systems-level change working with builders, decision makers, and users. And we hope to deliver a world where neuroscience can be trusted by all. And I have had the great honor of working with the GESDA community to advance its neurodiplomacy solutions. And it's with great pleasure today that I facilitate this discussion with a world-class roster of top thinkers and doers in neuroscience, diplomacy, and ethics. Advances in brain sciences, along with tools and technologies to measure, intervene, and stimulate the brain, are rapidly evolving. Some of these technologies can have tear-jerking, awe-inspiring impacts, such as helping someone with disease or catastrophic injury regain independence to walk, as you heard yesterday, or even restore abilities to communicate with loved ones, as you'll hear more about today. And these unprecedented extended abilities include non-humans as well. For example, laboratories have created new engineered clusters of cultured human brain cells that can be connected to robots, as well as genetically engineered brains that can augment cognitive and emotional capacities in non-human primates, as you'll soon learn. These advances promise a future where untold suffering can be relieved in ways never before possible. And that's a future we want. But we also want a future where we are not blindsided by the fundamental ways in which we view ourselves and relationships with one another. Intervening with the brain is to intervene with the most fundamental organ driving our thoughts, feelings, and cognitive experience. Intervening with the brain comes with great power, and with great power comes responsibility. Important advice that we've often heard given to superheroes. While some of these interventions promise restoration of function of those who aren't ill, these same interventions could be used to augment function in those who are not ill or are not yet ill. The line of what is considered disease versus augmentation is a blurred one at best, and we have historically seen how technologies have changed and moved the target of that definition. What is considered normal when it comes to rapid advances in science shifts. For example, we can imagine a future where the fundamental experience of aging itself is considered by society to be a disease. And unlike other technological advances, such as social media or even AI to some extent, where governance is struggling to catch up with a runaway train of how entrenched these tech are for how we interact as people and as nations, when it comes to neuroscience, we still have time to anticipate the future and shape the present. So today we'll explore neuroaugmentation and what ways using an anticipatory lens could influence global governance and global cooperation and empower our collective agency for a better future. And now I'm also going to remind you before we get started that during and after this session, you can contribute to the conversation on social media by using hashtag GESDA Summit. Now, as the GESDA methodology dictates, we'll start grounded in the science with a commitment to increasing our shared horizons of knowledge. Drs. Pooh and Henderson's talks will share the state of the art in their perspectives on anticipated future implications, as well as how to distinguish the hope from the hype. They'll also speak about what scientific and societal hurdles that must be overcome in order to reach the maximum potential of this work. Now, all of our GESDA speakers as you've seen, have CVs that could fill an entire session. And I encourage you to go to GESDA's speakers profiles on the website to get the full scoop. But I'll introduce our speakers in brief in the interest of sharing and dialogue. So first, it's a pleasure to introduce Dr. Jamie Henderson. Dr. Jamie Henderson is the director of the Stanford Program in Stereotactic and Functional Neurosurgery. As one of the developers of the field, Dr. Henderson is one of the world's foremost experts of deep brain stimulators for movement disorders, epilepsy, pain, and psychiatric diseases. His major research focus is on brain-machine interfaces for the restoration of movement and communication for people with severe neurological disorders. Please join me in welcoming Dr. Jamie Henderson.
Thanks, Karen, and thanks to the organizers, and thanks everybody for getting up early to join us in this session. I'm going to talk today about my work in brain-computer interfaces for communication. And we'll start off with this gentleman who I'm sure everybody in the room knows. This is, of course, Stephen Hawking, one of the most brilliant physicists of our generation. He was affected by ALS, which took away his ability to communicate and to move. He was, however, able to communicate with a device. His brain looks very similar to yours or mine. The problem with his nervous system lies in his spinal cord and in his brainstem, where the signals from the cortex are interrupted and no longer allowed to go out to the periphery to do useful things in the world. So the question is, what happens to the cortex? Are there still signals there that we can leverage? It turns out that, in fact, there are. So even years after paralysis, we can detect signals from the cortex, run them through a computer system, and then turn them into digital signals that we can then send back out to the world to do useful things, like move a robotic limb, as we saw yesterday with the wonderful work from EPFL, or to provide a communication prosthesis, which is one of the main things that my laboratory works on. We work with these tiny arrays of electrodes which penetrate just into the outer layers of the cortex. This is a 4 by 4 millimeter array with 100 electrodes that nestles down among the neurons and reads out information from individual brain cells. So brain cells communicate by electrical impulses called spikes. So as you can see here, each of these electrodes can pick up one or many neurons and read out those spikes. We can take those spikes, those electrical impulses, send them out through a wire bundle cable, amplify them, and then send them out to the real world where we can analyze them with a computer. So this is what this looks like. There's a pedestal which attaches to the skull, which allows us to interface with this device. And this is what a typical panel of those spikes looks like. Each one of these is either one or several neurons in the brain that are spiking with activity as we attempt to make a movement or do something with our brain. So it turns out that these spikes convey information by firing faster or slower. So if we look at an individual brain cell, and we at each of these individual channels, fundamental research done in the 1980s shows that, for example, here with a monkey doing a delayed reach task where he's reaching to a target, each of those neurons fires faster or slower depending on that direction. And so, as you can see here, each of these dots in this figure is a neuronal firing. And as you can see, as the monkey is reaching towards the left, they're firing more quickly, and when he's reaching to the right, they're firing more slowly. And so we can, if we look at this across that entire array of electrodes, this tiny array, you would expect that things would look pretty similar because it's in a very small area of the brain. But it turns out that this is not the case, that each of these neurons is tuned to a different direction. So we can leverage this information. If we depict each of these neurons or each of these channels with an arrow that indicates its preferred direction, if we place a cursor on a screen and ask our research participant, whether it's a monkey or a person, to move to that cursor, those neurons fire faster or slower and allow us to move to that target. So we were able to leverage this concept in this demonstration that we published in 2017. So this is one of our research participants, a woman with ALS, who is using this system to type out a message on a screen letter by letter. She's imagining moving that computer cursor with her arm. And as you can see across the bottom, there's a graph that indicates her correct characters per minute as she's moving along and answering the question that we asked her: how did she encourage her sons to practice music? So she was able to use this in a useful way. So we felt that this was really an advance that allowed for the potential for people with paralysis to communicate. But there are even better ways to do that through, for example, natural speech. Speech is an amazing thing that we can do as people. It's an exquisite motor control problem, thinking about how do the muscles move, how do all of these articulators allow us to produce, in a completely unconscious way, speech. But there's also a large translational need for these devices to help restore communication for people who can't speak. And so, based on some very beautiful fundamental work from our colleagues at UCSF, we decided to attempt this same sort of implant that we had accomplished in the hand or the upper extremity areas of the brain in the speech areas of the brain. And so by, again, placing these electrodes, in this case 8x8 electrodes, into the area of the brain that's specialized for the production of speech, we're able to once again obtain neural recordings from a large population. And here, what this is illustrating is each one of the dots on this graph shows the firing rate of those neurons and how specific or selective that they are to individual movements, so the forehead, eyelids, jaws, lips, or tongue. So we're able to decode this information from this area of the brain, including phonemes and words. And so we can then leverage this information to restore communication. So this is another one of our research participants with ALS who's lost the ability to speak intelligibly due to her disease. We were asking her, we're having her repeat these sentences on the screen. So you'll hear her attempting to talk, which you really can't understand what she's saying. The computer will decode the activity in her brain and produce, and what you'll see below is the computer's interpretation of what her brain signals are telling us.
I don't want to call her a babysitter. That would be good.
We can also ask her questions. Instead of just having her repeat sentences on the screen, we can ask her, for example, what are you proud of? And she can answer freely.
I am a very good friend and sister.
And in fact, this even works without vocalization. So here you'll see her mouthing words, not vocalizing, and again, repeating a sentence. This is actually easier for her because she has a difficult time with phonation. It's very tough for her to produce that. And so for her, this is actually easier.
I do not have much to compare it to.
So this is where we are. This is the state of the art now, allowing people to communicate with full vocabulary at the speed that they prefer to communicate at. In her case, it's about 62 words per minute. So where are we now, and what is going to happen in the next 5 to 10 years? Well, technology is moving very quickly. We'll soon have wireless, fully implantable systems, higher channel count. What we've shown in our laboratory is the more channels that you can get, the more brain cells you can read out, the more accurate and the quicker the decoding is, and better biocompatibility. So we need for these systems to last for decades, for the entire life of the person who has the implant. But perhaps more important is advancements in neuroscience. We have to better understand how language and cognition are represented in the brain, and even potentially understanding consciousness. So there are efforts in a number of labs across the world that are looking at these very problems. I think really the limiter here is the neuroscientific questions. The technology has been demonstrated. We know that we can do this. So how do we advance to the next level? So how are concepts and language represented in the brain? If you listen, for example, to Elon Musk, who predicts a future where we'll be able to communicate telepathically by transmitting our thoughts to others' brains. It makes one wonder, well, what is a thought? How do we actually communicate things between people? Well, we have to understand how that's represented. How does the brain do that? Can we ever really understand it? I mean, I think that's a fundamental question. And what scale is needed for us to be able to accurately decode? Would we have to record from every single neuron in the brain in order to understand this, or would that actually hinder our understanding? Do we need to simplify things to a much more human scale? Is mind reading really possible? There's been some work that shows that semantic and conceptual maps are broadly distributed throughout the brain. This is work that's done with functional MR imaging, which has really begun to reveal how this information is structured in the brain. And it turns out that there's a lot of territory that's dedicated, unsurprisingly, to understanding and communicating concepts. But there's been some very recent work showing that you can, by using functional MRI, you can begin to extract meaning from the brain using new artificial intelligence tools. So this just shows a recent study in which fMRI was used to extract stories which are being read to a person from the decoded stimulus. So the actual stimulus is over on the left, where they're telling stories about for example, getting up from an air mattress. And some of these are exact matches, some just get the gist, and then, of course, some are errors. And this is all done by extracting information from the functional imaging at the time. So I think beyond 10 years, once we start to look down toward the future, I think BCIs, brain-computer interfaces, are going to provide increasingly sophisticated readouts of brain states. The question is, how will they be used? Restorative, I think, that's where I live, in the restorative realm, trying to restore function to people who have lost it. But there are many people who talk about augmentation. Is it even possible to use these types of systems to augment human capability? I think the jury's still out on that. We're still struggling to even get back to able-bodied performance, let alone augmentated performance. Are there fundamental limits? I mean, how far can we go with the technology? I think, as I'm sure Karen will address, what are the ethical issues for augmentation? And it's important to understand that the technology is moving very quickly, and I'm personally very excited about it, but we have to be very careful about hype outrunning our actual understanding. I think there are some cautionary tales from the past. This is a quote from Alex Lewitt, the president of Vacuum Cleaner Company, who in 1955 said, "Nuclear-powered vacuum cleaners will probably be a reality in 10 years." So we don't want to go out on a limb and say something like this when, of course, this is absolutely ridiculous. But we have to be careful not to take the opposite, altogether too pessimistic view, saying something like this, that flight by machines heavier than air is unpractical and insignificant, if not utterly impossible. So thanks very much for your attention, and thanks to all the people in my laboratory who actually did this work and allowed me to present it here today. Thanks.
Thank you, Jamie, for kicking us off. What a wonderful way to start the day. Now for our next speaker, it's my pleasure to introduce Dr. Mu-Ming Pu, who is the scientific director of the Institute of Neuroscience at the Chinese Academy of Sciences and director of the Shanghai Center for Brain Science and Brain-Inspired Technology. His current research focuses on the use of non-human primates to study higher cognitive functions in human brain disorders, and he is one of the main organizers of the Innovation 2030 major science project on brain science and brain-inspired technology, also known as the China Brain Project. Please join me in welcoming Dr. Pu.
Good morning. Very glad to be here. I want to continue the subject that Dr. Henderson has introduced about cutting-edge neurotechnology. Now, we can, let's see, can I move forward? Okay. The neuromodulation technology, the BCI, or brain-machine interface that Dr. Henderson has introduced, can monitor, can decoding and manipulate human activity for medical purposes and or even for augmentation. But there's also drugs. The drugs that can enhance, repair the cognitive deficit or enhance the cognitive function, the cognitive enhancer drugs. Some companies are actually actively developing it. And there's also VR, metaverse, and GPT tools. I think this is the latest form of neuromodulation that's going to be even more effective, directly manipulate the sensory and cognitive function. Now, the danger of this is that although it's an augmentation that assists in scientific studies, in education, but it would, by having this assistance, the human brain will be deprived or gradually lose the ability to distinguish facts from fiction. And in fact, the main purpose of our human brain is to be able to determine ourselves, the events in the environment. If with this assistance, our ability will be homogenized and even affected in the long run. We may even lose our ability to interact with the environment correctly. And this is what will be the perils of the future neuromodulation technology. Now, there are also genetic and cell biology techniques that Karen has been mentioning for brain disorders. You can have early diagnosis tools that have been available to diagnose the genetic disease of the brain disease of all form. Now, the question is, what can you do about it if you find it out? Who keeps the information? Who should do the genetic diagnostic? This has also always been a debate. If we don't have a cure, why should I know about my disease? And this is the problem with this new technology. But now on the scene is a cell replacement technology. You can transform cells in the brain by genetic approaches. You can change glial cell to replace, to change them into neurons, to replace the lost neuron in stroke, for example. You can put stem cell into the region where you need the cells. And stem cell therapy has been used now for clinical trials for Parkinson's disease. Now you have a future on the scene, the genetic editing. You can edit in the genes that cause the problem in the brain or in other tissues by editing the embryo, early embryos, or you add in mature tissues by viral technology, locally inject virus to change the tissue. For example, one can imagine ALS will be cured by local injections of virus that correct the genetic defects in the spinal cord or in the motor neuron area. Now, these are the things on the scene. Now, there's a particular interesting area of research in non-human primate studies, because all these neuromodulation techniques, you need to try it out on animals closer to humans before you apply on humans. The preclinical animal studies using non-human primate is going to be very important for all the neuromodulation technology. And so there are genetic edited monkeys who express different human disease now. In the past, we were mostly using mouse disease of Alzheimer's or Parkinson's or all kinds of even depression model for mouse model for depression, but those are not very close in their symptoms to humans. So you need to develop new technologies. And human cell and tissue xenograft, grafting human cells into non-human primate would be a way to test how the human cell could be surviving in a primate tissue environment. And that's a prelude to the cell replacement technology. You can produce a human monkey chimeric to develop human organs in monkey to see if that could be used for future organ transplantation. People have been doing this in human pig chimeric with some success, but not very long survival. But the efforts are now ongoing for human monkey chimeric, which might be even better. So these are the future technology. The ethical issue obviously has to be considered. There's a recent guideline offered by the Chinese Society for Psychiatry and Chinese Medical Association on the use of neurotechnology, in particular brain-machine interface, brain-computer interface. Now, I don't want to go to the details. Their goal is to set up a guideline for the use. defining what actually BCI consists of, and how do you define effective, useful, safe BCI, and how the what type of people should be participating in this type of research. Most of the BCI research is in the clinical stage. And in this stage, there are ethical issues to be dealt with. And also, there are some bases that one has to follow. For example, there's a general consensus around the world. The World Medical Association has some guidelines, and every country are considering their own guideline. And how do we have a uniform consensus around the globe is one of the issues I think we need to consider. So there are, for example, there are 6 particular criteria for BCI research. Consider is whether this procedure is scientific sound, whether the design is rigorous, whether this really brings a benefit to the maximum benefit to the patient or for general public, whether the autonomy of the right to know by the subject and the decision of the subject is considered and respected, and also the procedure creates a minimum harm. Not only produce the augmentation or modulation tool at the present, but in the long term, short-term and long-term benefit to the patients or harm to the patients needs to be considered. And also the privacy protections and failures in selection of the patient, etc., etc. So I don't want to go in detail. I want to introduce the area that of my close interest is how do we use non-human primate to study potential of neural augmentation technology. Now, this is the standard way of manipulating a monkey to produce phenotypes so that we can study. For example, take the human oocyte injected with sperm, do in vitro fertilization. So we develop fertilized eggs in one-cell stage. You inject gene editing tools like CRISPR-Cas9 or base editor to change the gene in the nuclear gene or mitochondrial gene. So the embryo can then develop in vitro to some stage and then implant it in the surrogate mother to give birth to the monkey. Now the monkey, you can produce monkey to have phenotype. A good example is we knock out or delete a particular gene controlling the circadian rhythm of the animal. This is called BMEL1 gene. It's one of the several well-known core genes for controlling the daily rhythm of the metabolism and the human activity. Now, the BMEL1, when knocked out, the monkey loses sleep. It has this sleep disorder. That's what we expected. In their bloodstream, the cyclic variation, daily cycle variation of the neuroendocrines, like melatonin, like the hormones controlling the anxiety state, are varying with their daily variation is flattened, dampened, and somewhat wiped out. In the phenotype here showed that the monkey had great changes in locomotion. They move they don't move very much. Let's see. They don't move very much in the cage. They tend to hide in one corner of the cage, refuse to interact with people. There is anxiety and depression phenotype that we can identify, like very close to human. They don't interact with other monkeys. They are afraid of people. All these are psychiatric phenotypes. So this monkey also show some evidence of the schizophrenia phenotype. If we monitor EEG, the typical EEG pattern for schizophrenia patients are shown on this monkey. So this monkey are used for to do testing. But the problem is, as you can see, the different monkeys show with the degree of knockout or effective gene editing, they are varying among them. Very much, a lot of variation because of the genetic background of the oocyte, of the embryo are different. So their phenotype are different. the editing efficiency is different. So we thought a few years ago that the best way to have a good model, like in mouse model, you have a genetic uniform by inbreeding many generations, which is to create clones. The monkey clone, we succeeded in doing that in 1918, create the first two monkeys, a normal monkey cloned by fibroblasts from a female fetus, aborted fetus. Now, this monkey are alive well. Now it's now 6 years old. They are very, very healthy. So they are genetically identical. You can demonstrate. We can test their gene. They are produced by replacing the fibroblast nucleus, replacing the oocyte nucleus with the fibroblast nucleus, which are uniform. So you have identical clones. So we then take this circadian rhythm knockout monkey, the monkey that has a problem, depression phenotype. We take his skin cells, take the nucleus of that skin cell, inject it, replace the oocyte nucleus in 5 oocytes, and create a group of monkeys that are cloned. Now, these monkeys are very useful for testing. And the monkey shows the genetic phenotype or the psychiatric phenotype of their donor monkey. So they have this depression, anxiety phenotype hiding in the cage. And they are now used for neuromodulation technology and drug treatment. So all this shows that we can use effectively this study. But finally, one important thing is that scientists are interested in how human brain evolved, where we have such a capability. A recent study is by expressing a human developmental-related gene called microencephalin-1 gene, which if you have a defective gene, you have a small brain. Right? So normal gene, normal human MCPH gene, if you inject it or express it in monkeys, monkeys show the slow development of brain, the so-called neoteny of the brain. That's a characteristic of the human development, allow humans to have a prolonged childhood, to learn from the environment. This neoteny comes from many of the development genes, including MCPH. So the monkey shows human phenotype. It even a slow development, but it shows higher cognitive function in the working memory. So now we have an understanding that we can see how monkey can be used for studying how human brains actually evolved to acquire its capability. Now, this is obviously created a lot of concern. There's a headline in the newspaper saying that this is the Planet of Apes scenario, right? You are manipulating monkeys, but from the basic frontier science point of view, this is what we need to do to understand the human brain, evolution of the human brain. So finally, I think I should just keep we should have a global consensus of ethics. Now, we have to balance the frontier scientific pursuit with the societal needs. We also have to consider the universal human values and the cultural and religious difference. Now, maybe we know there are general consensus in animal use, like 3R principle. That's a universal. But can we reach a universal consensus on how to use neural augmentation technology? And maybe there's a general universal code, and maybe there's a cultural and societal differences. There may be a secondary code that could be applied. So in any case, this is the thing that we are facing in the future. And finally, the very important thing that I want to mention is that the bridging the gap from our frontier studies and the scientific understanding of the society, that gap we need to meet. But also we need to prevent the over-exaggeration and over-hype of our progress, so that this unrealistic expectation comes from a society that the scientists cannot meet. Okay, thank you.
Okay, thank you. Wonderful food for thought. And as we take a few seconds to digest that, I invite our other panelists up to the stage, and I'll give a brief introduction of them. So we have Her Excellency Claudia Fuentes Julio, who is the permanent representative of Chile to the United Nations office at Geneva. Welcome, please join us. We have Professor Marcello Ianca, Professor of Ethics and AI and Neuroscience at the Technical University of Munich. And virtually joining us, I think at 2 a.m. her time, maybe 3 a.m. now, is Professor Nita Farahani, Professor of Law at Duke University. And there she is. Okay. Thank you for joining us. And thank you especially, Nita, for joining us at such a late hour. So at this time, we've gotten a lot of food for thought. And I'd like for our panelists who have been sitting in the audience to kind of reflect a little bit. So Jamie brought up that, and so did Muming, that the speed of hype might be faster than our actual knowledge in science. Jamie also posed the question of the paradox of whether the brain is up to the task of studying itself. With as many brain cells as there are stars in the sky, can we really get the kind of resolution to help us understand what's happening? And what is restoration? And with Muming, he challenged us to think about unified ethics guidelines that actually would give consideration to different religious and cultural perspectives on fundamental ways in which we imagine our relationship to the brain and the ethical implications of that. And also how to address disorders or technology that allows us to predict brain disease before there is even an intervention available. And also the challenge of using non-human animals to model and become closer and closer approximations to humans that begin to bring us up to the ethical issues, the same ones that we might start to experience when using humans. So I'll first invite, actually, Nita, can I invite you first to offer some reflections or reactions before we dig a bit deeper into our discussions with the rest of the panelists at this point?
Sure. So hi, everybody, and I'm sorry that I can't be there with you in person, not the least of which because it's 2:30 in the morning here, and so I would be hopefully adjusted to a different time zone. But I'm grateful to the conference organizers and to GESDA for being willing to host me virtually since I couldn't be there with you in person. I thought the presentations today were wonderful and really, I think, help do what any good conversation around ethics and governance really should do, which is to lay the factual foundation. And it's, I think, important that that's how GESDA approaches problems and how any organization or any governance body would think about really approaching the problem. I want to just provide a few reflections, really coming at it from a legal and philosophical perspective, since that's the lens by which I really think about these issues. And in particular, I want to focus on questions around privacy and identity, agency and responsibility, and the broad concept of cognitive liberty. And I'll pick up with a thread that Karen introduced, which is to say, is it really ever possible to map the full sense of self that we might be looking at from decoding speech or decoding thought? And the answer to that is it may never be possible. It may never be possible to fully understand the concept of self or the full concept of thinking or metacognition, thinking about thinking. We may be able to decode, for example, intention to communicate language or what somebody's imagining in a moment, but not how they feel about what they're imagining or how they're reflecting on it or the kind of multiple layers of depth of thought and self. I don't know, though, that fact is one that would fundamentally reshape how we think about what the issues are, both from an ethical and from a governance perspective. And so I'll lay out just a few thoughts for consideration for the panel and for the conversation. The first is whether brain data that might be collected today or in the future is uniquely sensitive. And I've thought about this problem maybe as a category that's a little broader than what neurotechnology might enable. I've thought about this as a question of, with different technologies, whether they're neurotechnologies or recommender systems that are being used through our interactions with technology, eye tracking technology that is being integrated into virtual reality and augmented reality, all of which are really trained to try to make inferences about our brains and mental experiences. Is that data uniquely sensitive because it tries to decode what we're thinking and feeling in a hidden way, in ways that we don't express intentionally to other people? And whether the data that we might gather from neurotechnology itself might even go beyond what is possible to gather from those other modalities. I think an anticipatory framework has to be, in many ways, laser focused on that question. And it doesn't have to get to the point where we can know every level of thought or every level of self or every level of introspection. Merely, I think, breaching what I think of as the final frontier of privacy, that space, the inner sanctum, the place for private reprieve, fundamentally changes our relationship to others in ways that we have to include within any ethical framework. I think it's also important for us to move beyond traditional models of autonomy and self to really be having more robust conversations about the concept of relational autonomy. And by that, I mean, we are in many ways co-evolving with technology, whether that's something like our mobile phones or the fact that I can join you all by a video feed today with earbuds in my ears. My understanding of myself and your understanding of me is mediated by technology. Whether we're losing our hearing and have different hearing aids, which change our perception of the external world, or we use a neurotechnology device, our relationship to ourselves and our relationship to the world is both in relationship to others, and our understanding of self is in relationship to others, as well as in relationship to technology. And I think understanding that concept of relational autonomy should be part of how we think about governance going forward and how we think about the ethical issues that are at stake. The framework that I've been using to explore this is more of a human rights framework than a traditional bioethics framework. And that's because I think that the language of human rights is more universal. It captures many of the fundamental values that bioethics literature talks about and bioethics principles talk about, including in the previous presentation about thinking about whether it's possible to get to a universal theory of ethics and governance. I think that human rights gives us that language and set of shared values. Cognitive liberty is the language I've been using to understand that as a right to self-determination over our brains and mental experiences. And I think about cognitive liberty in many ways as an organizing principle, a value that can and should be recognized as a human right that would direct us to update other existing human rights. And I say update because on the one hand, I think that existing human rights in many ways well evolved and well updated cover a lot of the issues and would safeguard us against a lot of the downsides of the technology, but also enable us to have access to the many upsides of the technology that Karen discussed and that others discussed today. But I also think that we need an organizing principle that human rights don't evolve on their own, that they don't evolve in coherence with other aspects of human rights on their own, and that there are a set of technologies that are developing from neurotechnology and other interrelated ones that impact our right to cognitive liberty. I think of cognitive liberty as both a right to access and change our brains, as well as a right from interference with us. And that would lead us to update 3 existing interrelated human rights: a right to self-determination from being a collective and political right to also an individual right that allows us informational self-access and a right to change our minds if we choose to do so, a right to mental privacy being explicitly recognized as a part of privacy, and a right to freedom of thought, already, of course, recognized as part of our international declaration on the UN Declaration of Human Rights and incorporated into our civil and political rights, but presently understood more narrowly to apply to freedom of religion and belief, that should be expanded to safeguard us against interception, manipulation, and punishment for our thoughts. So I'll leave it there for further discussion because I am eager to hear what my co-panelists reflect on the presentations we've heard today.
Thank you, Nita. Thanks for kicking us off. So, Ambassador Fuentes, in 2021, Chile became the first nation to unanimously approve a bill to amend the Constitution to explicitly address the challenges of emerging technologies. And clearly, the country is in an exciting phase. The bill will experience the test of implementation and offer important learnings for the world as it test drives anticipatory governance for technology. At this point, what are some of the challenges and opportunities for learning with your experience of implementing the bill?
Thank you so much for the invitation this morning. Let me start with some general remarks because I've been listening closely what the panelists have been talking, and then I can also give some highlights in relationship to the specific case of Chile. General remarks. I'm not a scientist. I'm a political scientist, which is a little closer. I have a PhD in political science and international studies. And even then, I feel like a fish that is out of the sea, that is the term. Every time I am in a more scientific realm. And I believe that is actually the feeling and the emotions of many diplomats because we have been talking about this. So let me put that as a starting point and why is that worrisome. Because I think in the experience of Chile, that I will come back later, it was precisely the very close and tight work together between scientists, politicians, and diplomats that made possible, this law in order to protect neuro rights. So we need to be working more closely together instead of, breaching the existing gap. That's my first comment. The second relates to human rights, which the previous speaker was mentioning, and also the notion of the possibility of universality when we are talking about this. Also, the previous panelist also was dealing with that. So I think I will be quite honest with you. I see this is quite difficult. In this year, we celebrate the 75th anniversary of the Universal Declaration of Human Rights, and that's shaking. If you come with me, we are at the Human Rights Council these days. After this, I have to go there. The discussions are very difficult. Even the Universal Declaration today, there are certain aspects that countries do not perceive as being universal. The minimum protection for the dignity of human beings is something that is questioned today in the international realm. I'm going right now to talk about a resolution about maternal mortality, which you could imagine that is something that we call all, have a consensus on. Well, it is not. We will vote the resolution, and it has 7 amendments, because several countries believe that there are certain aspects in the resolution that we cannot reach consensus related to, issues like sexual and reproductive rights and many other issues. So what I want to express this morning is, imagine if we cannot reach agreement on these issues, that are issues that we have been discussing for more than 75 years, let alone we will reach agreements on many issues to say that there are ethical standards in terms of how we do research on these issues. Issues that, in terms of how the protection of privacy, which is precisely, I'm not saying that it's not possible, and that we shouldn't strive to do it. I think we should. What I'm saying is that I think sometimes you need to take into consideration the current political realm, which is very polarized, in which the minimum standards that we thought that we held possible between, all the members of the United Nations are not necessarily there anymore. So the conversations that we're having these days in terms of how, to move forward with science are even more difficult in the political realm. So I want you to think that also, when you're working in your research. Why? Because the ones that we will be dealing and negotiating the treaties will be us. The ones that have to deal with these difficulties, it will be the diplomats. If the diplomats don't understand your research, if we are unable to see, what are your objectives, what are actually the benefits of what you're doing, and what also are the perils of these new technologies, it will be very difficult for us, to get really frameworks and that strive to the protection of all human beings. So that in general. So the concern that we have, from my point of view as a Chilean diplomat, and it's something that I have shared with other diplomats here in Geneva, it's about the wider discussion on the human rights challenges of the use and consequences of new technologies. And I think these are the kind of debates that we should be having these days. In particular, we are concerned about the ethical dimensions of those research. We are also concerned in terms of distributional, also in terms of who gets these new technologies, which countries have an advance in these technologies as opposed to other countries that don't have access to those technologies, the difference between countries and within countries in terms of having access to those technologies. Those are issues that are a great concern for countries like mine, Chile, and other developing countries as well. And we should have them as a conversation too. We are also concerned that the existing treaties, and in particular human rights treaty, do not necessarily offer the protection as we discussed today, in particular about the neurotechnological issues that needs to be regulated. And this is something that is worrisome and that we should be working together. So that more in general. The specific case of Chile, so I think it might be of interest. Towards the end of 2021, Chile, my country, became the first nation in the world to have a constitution in force that explicitly addresses the challenges of emerging neotechnologies. The modification of the constitution, I believe, could be seen as an important historical event, given that emerging neurotechnologies have the potential to gather data from our brains or even to manipulate them, thereby influencing what we think or what we do. The Chilean constitution, as it now stands, requires that technological development respect people's physical and mental integrity, and it states that the law must specifically protect brain activity and information related to it. The aim is not to, of course, is not to discourage technological innovation or neuroscientific research, but to ensure that these are carried out with full respect of fundamental rights and that the population is adequately informed about their effects. And let me finish, how was this possible? Because I think this is in a way how we move forward together. There was an important role in the case of Chile of the Senate Commission on Challenges of the Future Science and Technology and Innovation, which is a body in which the objective is basically of legislating and thinking in politics and in all emerging issues. This is a quite interesting feature actually in our Congress, in which it has been a space to debate about science. That has helped. So second, I think the link with epistemic communities, universities, and think tanks. In particular, we develop a very closely work with the University of Columbia, the Neuroscience Foundation, and other academic centers as well. That was very helpful. Why? Because politicians, the parliament, and everyone involved in the legislation process had an opportunity to clarify, the terms of what was being discussing, the objectives of what we were doing, and to understand also why this matters. Because what happens in relationship to many of these debates in my country, and I believe in many others, is that the politicians, and not let alone the population, doesn't really have the time to grasp what is really behind of these technological innovations. certainly the good aspects and also the ones that could affect them in terms of their protection. So I think the key here is to be able to work together, to find a way to bridge this quite increasing gap between science and politics, and this is actually a call. We need you. We need empirical data. We need your brains in order to, work together and being able to have better frameworks that are, in general, for the protection and the advancement of humanity. And I will leave it there because I have to run to the council, but thank you.
Oh, thank you very much for offering that. So thanks for sharing that experience and those insights. I actually want to jump back to Nita, because I think we've had a great discussion kind of getting into human rights framing. But I also want to talk about another important framing that GESDA uses, which is anticipation. And Nita, I know that I've known you to wear the hat of a legal scholar, that of an ethicist, a philosopher, and now one as a futurist. So could you share a little bit with us how that lens of this future-looking perspective can be practically useful in addressing some of these issues, particularly related to neural augmentation, which sometimes requires more of a future-looking eye?
Sure. Thank you both for the question, and I really appreciated the prior remarks. So, futurism is not about a crystal ball. It's about trying to anticipate risks before they arise. Karen, in your opening remarks, you talked about the fact that with neurotechnology, many of the risks that we might worry about, the most profound risks, are ones that we still have time to address. When you're trying to figure out what those risks are, it's important to do risk analysis. There's really wonderful risk scholars, but also frameworks by which you can both assess the probability of risk, the magnitude of risk, the time frame of risk, and then to be able to develop frameworks to address them. So, for example, you don't want to regulate too soon to stifle innovation, but you also don't want to allow technology to, follow the kind of let her rip approach. When I sat on the Bioethics Commission in the U.S. Under the Obama administration, one of the terms that we introduced into the conversation was around the concept of prudent vigilance. And this actually tracks well to both anticipatory governance, but also mechanisms that can be put into place, like adaptive frameworks and adaptive regulation. So the idea is that you take a middle ground approach. You start to lay out what the risks are and start to try to do forecasting using modeling, not just so it's a fact-driven and oftentimes mathematical modeling that you put into place that tries to forecast risk in the time frame for doing so, and then uses checkpoints at which you might have triggering mechanisms, for example, in legislation that would come into play, or oversight bodies that you would appoint that would be looking for specific types of risks or markers or advances in the technology that would trigger additional oversight that would happen over time. So I think an anticipatory framework, especially when it comes to emerging technologies, allows the kind of flexibility that you need for the innovation, especially in an area that has so much transformative and promising potential as in an area like this, whether we call that augmentation or therapeutic or simply transformational for humanity. When you recognize that there is a technology of that scale for society, but that also has significant risks, albeit at a longer time horizon for some of those risks to be recognized or realized at scale, you start to try to anticipate and then address and put into place adaptive frameworks that can really evolve with the technology itself.
Thank you, Nita. So, Marcello, I want to turn a little bit to thinking about global regulation, and what we heard a little bit about from Ambassador Fuentes was also this challenge of how to bring these groups together, how to decipher the signal from noise. This is how to decipher the real science from the hype. And this is something we hear from a lot of our diplomatic community. And I know you've been working in the space of global regulation, anticipatory governance of neurotechnology. What kinds of challenges, what tools have you seen existing out there in the national space, in the multilateral sense? What are some of the frameworks at play? And what are some of the gaps in being actually useful to someone like our diplomatic community?
Yeah, So thanks, Karen, and also thank you to GESDA for the invitation, and also a shout out for the great work that they're doing in the field of science and technology policy internationally. And science and technology policy is precisely what we're discussing here. And the interesting thing about neurotechnology is that there is a governance landscape that is shaping up internationally, I would say quite fast. So technology is innovating fast, but I think this neurotechnology is a good example of policy that is not just coping with technological innovation, but is contributing to the shaping of technological innovation. We see some kind of synchronicity, some kind of chronological alignment between the progress in technology and the progress in policy and governance. And I think this is something that we should emphasize. I think we can cluster the governance landscape on neurotechnology into three main categories. One is self-regulation by the scientific community. Another one is soft law instruments by intergovernmental organizations. And then, as we have heard from the example of Chile, we also have the first examples of legally binding frameworks. Now, self-regulation is a very broad definition, but what is happening is that a lot of international societies, professional associations, and so on, are attempting to introduce codes of conduct and ethical guidelines for the ethical use and development of these technologies. We have heard from Professor Pu what the Chinese Society for Psychiatry is doing. With the International Brain Initiative, we are attempting to develop a code of conduct for responsible sharing and processing of brain data internationally across the various national brain initiatives. The IEEE Standards Association is developing standards for brain-computer interfaces, and also industry actors are developing codes of conduct. A lot of companies in the neurotech space now have ethical codes that they are directly implementing in their day-to-day practice. At the level of soft law, we are seeing a lot of intergovernmental organizations being very active in the field. The OECD, the Organization for Economic Cooperation and Development, has been on the front line of this work. They have introduced in 2019 the first international standard called the OECD Recommendation on Responsible Innovation in Neurotechnology, which really introduces the responsible research and innovation paradigm into neurotech. And this has set a very high standard, I would say, internationally. And a lot of other organizations are also active in this field. If the OECD is focusing more on responsible innovation, other organizations like the Council of Europe and the United Nations are focusing more on human rights protection and promotion through neurotechnology. And finally, we have heard from Chile that some countries are pioneering the introduction of legally binding frameworks. Now, the question is, what challenges are we facing here? I think, first of all, we have to emphasize that the scientific community is very aware of the ethical sensitivity of neurotech. And I think all these examples, this increasingly rich landscape of governance tools that is emerging is the proof that both the scientific and the policy community are aware of this sensitivity. But on the other hand, there are some challenges, and I think the topic of our panel is a good example of the challenges that we're facing, because neuroaugmentation is, in bioethics, we draw a distinction between therapy and enhancement, between restoration of function and augmentation of function above baseline, so also healthy subjects that can improve their abilities. And this is a good example of something that is harder to regulate for a lot of reasons. First of all, because humans always augment themselves throughout our entire biological and cultural evolution. We have been improving our functions. We wear eyeglasses that improve our vision. We wear shoes that improve our locomotion. And we can improve our cognitive function with simple tools like having a better sleep habit or healthy nutrition. But now we have technologies that will probably allow us to do that in a more targeted way. And I think one challenge here is equality, because sleep and healthy nutrition are relatively evenly distributed, but unfortunately the technologies that we're talking about are not as evenly distributed. So in some cases, we're talking about expensive technologies that may not be available to everyone on Earth. So if in 20 years from now, we will have cognitive enhancement through neurotechnology or through drugs, as Professor Puas also mentioned, then I think an important challenge will be the equal access to the benefits of these technologies. Another challenge, in my view, is that all these frameworks that I mentioned before are domain-specific. So the OECD recommendation focuses on medical uses of neurotechnology. The report I wrote on behalf of the Council of Europe focuses on applications of neurotechnology to biology and medicine, because the focus of the Council of Europe is a potential revision of the Oviedo Convention, which regulates the preservation of human rights in biomedicine. And historically, if we look at the history of technology, we've been very good at regulating domain-specific technologies. You know, medical technologies are very well regulated. There are some glitches here and there, but they're very well regulated. Cars are very well regulated because they are a domain-specific technology. We develop traffic codes. What we struggle with are general-purpose technologies. So when we have technologies that can be used across many different domains of human lives, that's when problems begin. And we have seen that with social media, which are notably general-purpose technology, can be used for entertainment, can be used for communication, can be used for information sharing, and so on. And we have been, I think, incredibly bad at regulating social media, and now we're facing the consequences of that poor regulation. AI is another general-purpose technology. And I want to also say a word about this, because we are focusing primarily on neurotechnology, but we can improve our cognitive functions not only through neurotechnologies, but also by using, for example, AI as an external cognitive assistant. And then also the ethical implications of AI will affect neurotech. I just want to conclude with a few words about the future, because we have been hearing a lot of predictions and Nita's pioneering work on foresight studies and futurology. I think it's very important to this topic. It's very hard to predict where neurotechnologies will lead us in, say, 20 years from now. But we should also be mindful that 20 years are not a long time. I want to remind everyone that the first smartphone was introduced in 2007. That's 16 years ago. And it has completely revolutionized our society. Our society doesn't look the same as before smartphones were out there. We have created an entire economy that is based on that. So will neurotech follow a similar trajectory? It's hard to tell. But it is at least a possibility that we have to consider, especially given the rapid progress that AI is introducing. But we have to have an evidence-based approach. So to avoid the hype, we really need to have boots on the ground in the field of science, look at the scientific evidence, and develop governance frameworks that are adaptive. So if the technology is adaptive or near-adaptive, as we have heard from Jamie, well, then also the governance framework has to be adaptive to these challenges, and we have to be able to have models that are sufficiently agile to adapt to the trajectory that technology will take in the future.
Well, thank you, Marcello. So in some of these governance conversations that you've been participating in these days, I'm kind of curious, and I'm curious from Nita too, and then I want to turn to closing with Jamie and Muming. You talked about some of the challenges both of you have. Who is missing from this conversation? And Ambassador Fuentes also talked about the challenges in bringing these groups together. What mechanisms are missing? What voices are missing from the conversation in your experience thus far? Can you speak a little bit about that? And Nita, maybe you could start, and then Marcello.
So it's a great question. I mean, one of the challenges of a process of democratic deliberation is, I think, stakeholders change over time as the applications of a technology change over time as well. Earlier in the process, oftentimes it's primarily researchers who are at the table. You may have ethicists who join in the conversations, and this is a context in which there are far more ethicists, I think, who've been part of the conversation from earlier stages. patients have increasingly been at the table, and so have families, which I think is important. Patient advisory groups have been at the table, which is helpful. Funders have, in some instances, been at the table, and increasingly, I think some of the commercial entities who are in the space. I think as the risks evolve and as the conversations broaden outward. So, for example, Marcello, just at the end of his remarks, talked about AI, and this is a conversation that increasingly, there's National Academies workshop that's starting to develop around the intersections between neuroscience and artificial intelligence. The implications of neurotechnologies and the governance of neurotechnologies, I believe, has to be thought about not just in a domain-specific way or just in a country-specific way, but more broadly, understanding that it is a set of technologies that are addressing and raise common risks. And I think what's missing at the table is a conversation that's really much more integrated across different domains. So, for example, the increasing use of eye tracking or the possibility of using neural interface technology as part of virtual reality and augmented reality, the ways in which AI and neurotechnology are co-developing in many instances mean that there are domain-specific governance conversations that are happening in each of those areas: metaverse governance, immersive technologies, AI technologies, but there's very little cross-dialogue that's happening across those different domains. And so I'd say, there are many different stakeholders who will emerge over time, but one area is to not have redundant and in many cases conflicting governance approaches to technologies that are intimately interrelated to one another.
Thank you, Nita. Marcello.
Well, it's hard to add something relevant to what Nita said, because that was a very comprehensive answer. But I think probably what is missing in the current landscape is a bottom-up approach that would complement the top-down approach. The work of intergovernmental organizations has been great in this field, but intergovernmental organizations are, ruled by delegates that are also inviting experts at the table, but the general population is currently not participating in the general debate on the governance of neurotechnology. And I would say, in some sense, is understandable, because these technologies are not so distributed, so a lot of people may not have formed an opinion because they don't use those technologies. So, but for example, patients already do, and having patients at the table of governance discussion, I think it's very, very important. And in the future, as these technologies become more widespread, I think also the general population should be participating, and we have to create platforms for democratic deliberation on these technologies. I think already in the field of AI, we do need badly platform for stakeholder engagement, and you have been doing such a great work on stakeholder engagement in the field of neuroethics. I think, for example, in the field of AI, we should do more to have a democratically accountable deliberation on the governance of these technologies. And when we create these platforms, we have to make sure that there is also a sufficient degree of information and awareness about these technologies, because you cannot make decisions in a democratic state, informed decisions, without having access to information in the first place. And I think also it's very important that us as a scientific community, but also as a policy and diplomatic community, do some work on raising awareness and trying to spread the information that we generate. And I think in academia, we are usually not good at it. We try to stay in our ivory tower, but I think platforms like this one are very important to raise awareness on the topic.
Thank you, Marcello. So I think we're hearing a little bit about this theme of the important role of these different voices, a bottom-up process. And one thing that Ambassador Fuentes mentioned also was the important role that scientists actually took in establishing or advocating for that new bill in Chile, which is a success story for thinking about the connections of science and policymakers. I want to turn to Jamie and Muming at this point, who have been sitting patiently and digesting this information. And we know that scientists are rightfully trained in this systematic methodology, conclusions that are based on evidence and probability or statistical significance. And actually, many of the things that a good futures or anticipatory work does. But what we often hear from scientists is that kind of anticipating the future can feel almost antithetical and to what they're doing. And this hesitancy to anticipate, present company excluded, ends up being faced with a void where instead we have the fevered reflections of those who are not neuroscientists, but instead maybe entrepreneurial billionaires or those with a strong attention-grabbing media acumen. And then for the public and for policymakers who are struggling to grasp hold of what might be the future, they become the voice of brain science in the future. So what roles can scientists play in anticipating some of these opportunities and the risks for policymakers that they should be knowing about, or even preventing premature regulations from a top-down approach that might unintentionally hinder science that could benefit the community? Can you share a little bit on your reflections on that?
I'm happy to jump in on that.
Thank you,
I think so. There are two parts to what you just said. One is what role do we play, and I think communication is really important. I think too many times scientists don't take the extra effort to try to communicate what they're doing to the public. I think that's really important, and I don't know how to broaden that. I don't know how to encourage others to do so. I mean, in my own laboratory, I try to encourage it, and I think it's an important thing moving forward. But I think the second thing that you said, which I really resonated with, and many of the panelists have talked about this, but I resonated with what Nita said in terms of, perhaps having a dynamic regulatory or oversight structure. So I think I would really implore policymakers and regulators to try to keep a light touch when you can. Innovation is important, but it's also important to make sure that you can, that's why we're here, right? To anticipate what's going to be coming out of the laboratory and try to catch it at a stage where you're not stifling that innovation. It's really important not to do that, but you're also making sure that there's both awareness and oversight of how those things get out of the lab and into the public sphere.
Thank you, Jamie.
Well, I think the next 5, 10 years, maybe 25 years, we have a very urgent problem of defining what's abnormality in brain function. Now, we don't, if we talk about my cardiovascular system, I know I have a high blood pressure because we have a quantitative criterion for my blood pressure, high 140, low 90. If I'm above that, I take pills. But I don't know my cognitive function. What's the normal cognitive function for my age? My working memory, my long-term memory, am I below the curve or above the curve? So there's actually a complete absence of the normal cognitive function, quantitative criteria for normal cognitive function of various ages among various populations. Now, if we don't have that, how can we say we need to augment it, whether we are repairing it? Because we wanted to define the use of augmentation in the medical repairing purposes or for augmentation purposes, right? So now you need this normal curve, normal distribution that we don't have. I think the scientists probably should really work hard on it. And in fact, in China, we are instituting a large-scale brain cognitive examination in our annual health checkup, brain health checkup for general populations, not for patients. Now we want to have a quantitative number of all the cognitive functions, sensory function, cognitive function, emotional parameters, so that we have a number. Now I think we need a global consensus of definition of what is normal and what is abnormal before we can have a global governance of the use of augmentation technology, right? So in fact, we are hoping in 5, 10 years, we'll have a normal curve for large population. So we can define who needs cognitive augmentation and how do we apply this technology effectively.
Thank you. So with that example and in closing now, I invite the provocation for you to think about what, given this rapid acceleration of technology, given some of the voices that could be involved, given the need for a transparent and rigorous process and global cooperation, what is the role that you might think GESDA could play in bridging some of these gaps and addressing some of these challenges? And I think I'll start with Jamie and Muming, and then we'll move around from Marcello and close with Nita. The role, who can play, you say? Is that for GESDA? GESDA, yes. Yeah, I mean, certainly, I've been impressed with how precise some of the predictions and outcomes can be when we all focus on it and communicate together. So I think GESDA is on the right track, in my opinion. I think the science radar and integrating that into events like this, I think will to bring together policymakers, scientists, diplomats. I think it's the right way to do it. Thank you, Jamie. Muming?
Yes, I think GESDA will be very useful in pioneering these international conversations on the future technology. I think this is really an area that needs more discussion among scientists in all sectors of the society, all the stakeholders, not just the policymakers. I think there are discussions at the United Nations and a higher level discussion, but the participation of scientists and especially people who are working on frontier, who knows the technology, how it's developing, to be really actively in discussion. That would be great. Thank you. Marcello?
Well, I would say probably three things. So one is what Professor Burst just said, so creating GESDA is really becoming a catalyzer for an international global debate on emerging technologies. And I think this is really important because we need this kind of international platforms where the global community can convene. The second one is definitely the focus on anticipation. I think it's we can probably have a consensus here that anticipation is very important, that we cannot just catch up with powerful technologies, but we need to steer the development of these technologies, which doesn't mean introducing limitations on use, but actually it also means accelerating the development of technologies that can produce benefit for hundreds of millions of people worldwide. And the third one, I would probably say GESDA is really pioneering a broad focus on many different technologies. And our session is about neurotech, but other sessions in other rooms will talk about quantum, we'll talk about synthetic biology. And what we are experiencing in the last few years is that all these technologies are converging. Now we're talking about as if they are discrete categories, but they're not in silos. AI is not different from neurotech because currently, it's very hard to have neurotech without AI. And many other fields are also converging. And people have been talking about converging technologies for the past 10 years. And I think GESDA is one of the very few platforms that is enabling this broader debate on technology.
Thank you, Marcello. And Nita?
See, now I have the unfairness of following Marcello this time. I understand. No, I think that my co-panelists have said it well. I would just add one small piece, which is recognizing both the good and great contributions in anticipatory frameworks that are cross-cutting across different technologies. I think pairing that with really great examples of agile governance that can adapt to that anticipatory framework would be really valuable. So everybody likes to talk about agile governance. There are only a few really great examples out there so far that have worked, and they've had really specific milestones and interim analyses on which they could be based for invoking the different trigger mechanisms for different stages of the governance. And so I think helping to pair an anticipatory framework together with different models of agile governance would be a really valuable role to play.
Okay, great. Well, I want to thank all the speakers for their contributions and the audience members for their patience and engagement. And if you haven't gotten enough, and you probably haven't, you can continue the conversation on with hashtag GESDA Summit on social media. And you actually can attend right after this a session in Auditorium B, Defining the Red Line. And after lunch, Augmenting Consciousness and Psychedelic Medicine in Auditorium B. So thank you for your time, and have a great day. Thank you to our speakers. Thank you, everyone.